All right, let's jump right into this explainer. Look, every single time you use GPS to dodge traffic or you check the weather radar for a weekend storm, you are relying on space tech. It's just a fact of modern life. But here's the thing. When we think of space, our minds immediately go to roaring rockets, right? Or astronauts, or those gleaming satellites orbiting hundreds of miles up. Well, today, we're going to completely shift that focus. We're looking away from the satellites themselves and pointing our attention straight down to the massive hidden terrestrial infrastructure and those invisible communication links that actually make every single space mission possible. To really wrap our heads around this massive technological feat, we're going to take a bit of a journey. We'll start right here in the dirt with the physical ground hardware, travel up through the invisible radio frequencies, take a peek inside the human nerve center running the whole show, and finally blast off to see how these things actually navigate their orbits. So let's kick things off with part 1, ground station architecture, the terrestrial link. The wild reality is that every single operational satellite up there is completely dependent on at least one facility down here, just to function. These ground stations are the absolute foundation of it all. They range from these small, portable units to just massively impressive, complex installations. And their relentless 24/7 job is to track satellites as they whip overhead, beaming up vital commands and pulling down the crucial data we need from space. It really all boils down to 3 core components working in absolute perfect harmony. First, you've got the antenna systems. That's your primary physical interface. Second is the RF, or radio frequency equipment, which is all your transmitters, receivers, and amplifiers. Honestly, think of this like a highly advanced, massively overpowered version of your home Wi-Fi router. And third, you have the control systems. These are the vital computer networks managing where the antenna points, processing the signal, and coordinating the whole shebang with mission control. And size absolutely matters here. A larger parabolic dish diameter gives you greater antenna gain, which basically means it can capture a lot more signal energy. That is a real game changer when you're trying to talk to distant satellites or pick up incredibly faint whispers from deep space. Plus, to maintain that crucial connection, these huge structures rely on extremely precise motorized mounts. They are constantly adjusting in real time just to keep up with a satellite screaming across the sky. Okay, moving on to part 2, satellite frequency bands, the invisible bridges. So we have these massive terrestrial dishes, but how do they actually speak to a chunk of metal hurtling through the vacuum of space? Well, they use this total alphabet soup of invisible bridges, and different frequency bands offer totally different advantages. Take lower frequencies, like S-band, sitting between 2 and 4 gigahertz. That easily punches right through the Earth's atmosphere using very little power, making it absolutely perfect for sending reliable commands. On the flip side, higher frequencies like K-band, way up at 26 to 40 gigahertz, can carry massive amounts of data. But there's a catch. They are highly vulnerable to rain fade. If you've ever lost your satellite TV signal during a heavy downpour, yeah, you've experienced rain fade firsthand. Now for part 3, mission control and TT&C, the operational nerve center. Let's head indoors for a second. We're transitioning from the heavy outdoor hardware to the human brains actually running the show. Unlike the hardware-focused ground stations, the mission control center is where the magic happens. It's where highly specialized teams of engineers are glued to telemetry screens, planning intricate maneuvers and keeping the spacecraft healthy. For the big, critical missions, this room is humming 24/7, with totally separate teams dedicated to things like power, thermal controls, and payload operations. And central to their entire job is TT&C. That stands for Telemetry, Tracking, and Command. This is an absolutely critical, heavily redundant subsystem. It operates completely independently of the satellite's main payload. Why? Well, because if the primary mission equipment breaks, this TT&C link simply has to stay alive. Without it, your billion-dollar space asset literally just becomes an uncontrollable piece of space junk. Let's make this real for a second. Imagine you were sitting in that control room. Suddenly, a bright red anomaly flashes across your screen. Telemetry shows your satellite's battery voltage just plummeted from 28 volts to 24 volts, and it is discharging fast. So, what do? How do you troubleshoot a high-stakes emergency hundreds of miles above your head before the whole thing just dies? The clock is ticking, right? You have to be incredibly methodical. You'd immediately demand detailed power telemetry. You might command the payload into safe mode to urgently kill the power draw, or physically tilt the solar arrays. And you're doing all this while frantically calculating your critical decision factors, like what is the exact state of charge? Can we switch to a backup battery? And most terrifyingly, How much time do we actually have until the satellite flies out of range of our ground station? Talk about pressure.
All right, part 4, launch and orbital operations. Getting to the final orbit.
So we know how to manage them from the ground, but getting them to their final destination, that's a whole different beast. Because liftoff is truly just step 1. Most satellites don't just get dropped off at their final home. It's a complex, multi-stage dance. First, they get placed into a stable, low-parking orbit. Then they execute an injection burn using their own onboard propulsion. After that, they enter a coast phase, just gliding along this massive transfer arc. And finally, they fire a crucial circularization burn to lock into their operational orbit. Depending on where they're going, this whole process can take days, sometimes even weeks. Finally, part 5, constellations and orbits, structuring space assets. So we've finally arrived in space, but where a satellite ends up depends drastically on what job it's doing for us back on Earth. It's a fascinating trade-off. Low Earth orbit, or LEO, sits just 500 to 2,000 kilometers up. It gives us lightning-fast internet latency, like 20 to 40 milliseconds, perfect for gaming or video calls. But because they're so low, their coverage footprint is tiny, so we need constellations made of thousands of them. Medium Earth orbit, or MEO, sits way higher, up to about 35,000 kilometers. You need far fewer satellites to cover the Earth, but the physics of that sheer distance introduces a delay, pushing latency to around 150 milliseconds. That's what gives you that slightly annoying lag on a Zoom call. But think about it. How do you make sure you never drop a call while these things are whipping around the planet at thousands of miles an hour? Engineers use something called Walker delta patterns. It's essentially a perfectly choreographed math dance in a vacuum. By symmetrically spacing satellites across multiple orbital planes, they basically guarantee that the second one satellite drops below the horizon, another one is perfectly positioned overhead to seamlessly take your data. It's just wild that this works. And that really brings our whole journey full circle. It's kind of mind-blowing when you step back and look at the sheer scale of it all. You've got these massive, ultra-precise ground stations, these invisible frequencies cutting through the weather, incredibly stressed human mission controllers working 24/7, and mathematically flawless orbital patterns. All of these moving parts completely rely on each other to form this delicate, synchronized global network that literally powers the modern world. But I want to leave you with one final thing to think about. As commercial space access gets cheaper and cheaper, thousands more satellites are being launched into these exact same orbits every single year. And they're all relying on this exact same terrestrial architecture. So we really have to ask ourselves, just how much more traffic, data, and frequency congestion can the hidden half of space operations handle before the physical limits of our Earthbound system just break? Definitely something to chew on the next time you look up at the night sky.